Intermolecular forces are why everything sticks to everything. It is why ultimately, if you cool something down enough, it will condense into the liquid and then eventually the solid phase. It refers to a stickiness quality. And we can appreciate many physical properties of atoms and molecules when we understand that these forces extend through the sample in all directions. As we increase the temperature of a substance, its kinetic energy increases. It becomes more significant as we move from a solid to a liquid to a gas. Conversely, as we decrease the temperature, the kinetic energy of the particles decrease, and there's an increasing significance of intermolecular forces. And this causes gases to condense into liquids and ultimately liquids to freeze into solids. We can best understand the role of intermolecular forces when we consider the interplay between kinetic energy and intermolecular forces. When we are in a gas, the attractive forces, or the IMFs, are very weak relative to the kinetic energy. These particles are very far apart, as we see here, and the gas has no fixed shape or volume. Temperature decreases and attractive forces become more significant because the particles have less kinetic energy. Thus, a liquid particles can flow over top of each other, but they have a fixed volume and they're constrained to the bottom of the container. When we are in a solid, our kinetic energy is very low and the attractions dominate the kinetic energy. It has a fixed shape and a fixed volume. We are very familiar with the consequences of intermolecular forces in our everyday life. We see what happens when we have a very cool beverage, perhaps we have ice in here, and there's gas particles of water out here in the atmosphere. They come in contact with the glass, lose kinetic energy, and we see condensation of these initially gaseous water molecules forming on the outside. In a lake, we have the cool lake. Initially, our air here is a little bit warmer. We lose kinetic energy as it comes in contact with a lake, and initially gas phase water molecules have precipitated out of the solution in the air and become mist that we see visible above the surface of the water. Intermolecular forces play a huge role in many physical properties. When the substance we're looking at has stronger intermolecular forces, we know it has relatively higher freezing point and boiling points, heat of fusion and heat of vaporization. These are energies involved with phase changes. Stronger IMFs also lead to a higher viscosity or resistance to flow of a liquid, higher surface tension, which is seen as a measure of a substance's tendency to minimize the amount of liquid surface it has, and stronger IMFs lead to lower vapor pressure. We'll have much more to say about vapor pressure in Chapter 11. Please remember that IMFs are weaker than intramolecular forces, or those forces that hold individual atoms next to each other, either covalent or ionic bonds. This is our intermolecular force, which is significantly weaker than these forces that are holding, in this case, the hydrogen and chlorine atoms together. The strength of IMFs varies considerably between different substances, and we can recognize these relative differences by identifying the types of IMFs present in a given sample. London dispersion forces, or LDFs, are present between particles of all substances. But they are generally the weakest form of IMF. Dipole-dipole attractions are a little bit stronger in general, but exist only between polar molecules. Hydrogen bonding forces are especially strong dipole-dipole interactions. They exist between molecules that contain an OH, NH, or FH bond. We will use the relevant abbreviations for these: LDFs for London dispersion forces, DDF for dipole-dipole forces, and hydrogen bonding we'll refer to as hydrogen dipole-dipole forces. It is especially simplifying to remember and recognize that all IMFs are electrostatic in nature. They have to do with the attraction between a positive and a negative charge. The difference between the different types of IMFs is the origin of those positive and negative charges. To appreciate dispersion forces, we remind ourselves that electrons are in constant motion, and on any given instant there may be an unequal distribution of these electrons. This cartoon represents a higher density of electrons on this side of this diatomic molecule than this side. This does not last very long, but long enough to induce a dipole in a neighboring molecule and experience an electrostatic attractive force between these two molecules. The relative magnitude of the London dispersion force depends significantly on the molar mass of the material and its polarizability. Polarizability is the measure of how difficult it is to distort an electron cloud. In general, the further away these electrons are from the nucleus, the more polarizable they are. And a larger polarizability leads to a higher degree of London dispersion forces. And these stronger LDFs lead to requiring a higher temperature or higher kinetic energy to break apart these particles. That's why when you have a more polarizable molecule, it's going to lead to a higher melting point and a higher boiling point. These cartoons illustrate the effect of these larger dispersion forces on the boiling point of some atoms, some diatomic molecules. These happen to be homonuclear diatomic molecules, and nonpolar compounds. So what we see is that an increased size leads to a larger polarizability, and therefore stronger LDFs, which overall means stronger IMFs. and higher boiling points. Okay, note that all of these illustrate the effect of polarizability on non-polar particles. Again, we have our atoms, homonuclear diatomics that are nonpolar, and these nonpolar hydrocarbons. Okay, please note though, there is a very slight difference in the electronegativity between carbon and hydrogen. Overall, hydrocarbons are considered to be nonpolar molecule. Here we're illustrating a more subtle effect of LDFs on boiling points, and that is how much surface area there is available for neighboring particles to interact with each other. Now note here we have different isomers of pentane, and since they're all pentane, they all have the same formula weight. However, we see in their realized boiling point that there are some differences here. Obviously, the intermolecular force is increasing when we go from neopentane to isopentane to N-pentane. The assertion is that the reason for this is that there's less surface area on the more compact molecules, less surface area for these particles to interact, and therefore a lower degree of London dispersion forces, lower TB, lower TF. Again, the explanation is that even though these particles have the same formula weight and they're all nonpolar molecules, neopentane is more compact, less surface for the interaction of LDFs, and therefore there will be a lower boiling point, lower freezing point. And here we see that manifested in the boiling point. As we go to a more spread out molecule, we have this increase in boiling point. Now we go on to the next type of intermolecular forces, and that is dipole-dipole forces. Dipole-dipole forces are the attractive forces that exist between polar molecules. Okay, in order to exhibit dipole-dipole forces, molecules must be polar. They must have a permanent dipole. We see this exhibited for HF. We have a cartoon here representing the electron distribution in a molecule of HF. Hydrogen is less electronegative than fluorine. Fluorine is going to gather an increased electron density, and a partial negative charge is associated. This side of one HF molecule is going to be attracted to the partial positive on a separate molecule. Because the source of the positive and negative charge is permanent, in general, dipole-dipole forces tend to be stronger than London dispersion forces. But occasionally, very large nonpolar molecules have stronger IMFs than polar molecules. What also remains true is that if we have molecules of similar molar mass, the polar molecule is going to have stronger IMFs than that nonpolar molecule. So LDFs in general are weaker than DDFs. However, if we have a very large molecule, the London dispersion forces may be a bit stronger than the dipole-dipole forces. Hydrogen bonding is the last type of intermolecular force of concern for us. The hydrogen bonds are those that occur between molecules that exhibit a oxygen to hydrogen bond, a nitrogen to hydrogen bond, or a hydrogen to fluorine bond. It's essentially an especially strong dipole-dipole force. So hydrogen bonding, hydrogen dipole-dipole forces are stronger than ordinary dipole-dipole forces. The effect of hydrogen bonding is illustrated in this cartoon. We see in this group of compounds here is that as the molecular weight increases, we see a corresponding increase in boiling point, and this is what we would expect. Okay, so we expect that as formula weight increases, there is a corresponding increase in boiling point, and this is borne out. Okay, however, we have these anomalous points up here, and we notice that they all contain either nitrogen, hydrogen, hydrogen fluorine, or hydrogen oxygen bonds. These are especially strong dipole-dipole forces, and they result in an abnormally high boiling point for these compounds for such a small formula weight. Absent hydrogen bonding, we see a predictable increase in boiling point with an increase in molar mass. However, for these compounds, even though they're much lighter than any of these other compounds, they have an anomalously high boiling point, explainable by the presence of an exceptionally strong intermolecular force we're referring to as hydrogen dipole-dipole forces. Intermolecular forces also have a very strong impact on the property of solubility. The golden rule of solubility is that like dissolves like. What that means is that nonpolar solutes tend to dissolve best in nonpolar solvents. Polar solutes dissolve best in polar solvents. The underlying physical basis for this observation is that things are most mutually soluble when they have very similar IMFs. Let's look at the particle interpretation of making a solution. We start with solvent particles that are all mutually attracted and solute particles that are mutually attracted. In order to start to make the solution, these particles have to be separated from each other. So we have to overcome the solute-solute particle interactions, the solvent-solvent particle actions. So we essentially have these separated particles. And then these particles recombine and form new interactions between the solvent-solute. And again, things are mutually miscible when the interactions between the solute and the solvent particles are very similar in energy between those of the solute to solvent particles. Things that are nonpolar have similar intermolecular forces and therefore are mutually soluble. Same is true for nonpolar substances. So like tends to dissolve like. So let's apply our general principle of like dissolves like. And we can restate it. When you have solute-solute particles and solvent-solvent particle interactions that are comparable to those between the solute to solvent, these things tend to be mutually miscible. Substances that exhibit similar IMFs can most readily form solutions. So let's apply this. We have some compounds, carbon tetrachloride, ammonia, hydrogen fluoride, and oxygen. We wanted to determine which is water soluble and which should have limited water solubility. First, let's remember that water is a polar solvent. The structure of water is bent, leading to the ability to draw a single line that distinguishes between the negative and the positive ends of the molecule. It's a polar molecule. We would expect it to be able to dissolve polar substances best. To determine if a molecule is polar or nonpolar, we have to consider both whether or not there's polar bonds that exist and the molecular symmetry of the molecule. For example, carbon tetrachloride contains polar bonds because carbon has a lower electronegativity than chlorine. However, its tetrahedral geometry overall and its dipoles cancel. So overall, carbon tetrachloride is a nonpolar molecule with polar bonds. Ammonia is a polar molecule. It has polar bonds, but it has trigonopyramidal geometry, which means our dipoles do not cancel, and it's a polar molecule overall. HF and O2 are much easier to predict polarity. HF is linear, there's only two atoms, and therefore its polar bonds lead it to be a polar molecule. There's only one dipole, they can't cancel. O2 is the only one of these that has nonpolar bonds, and therefore it is a nonpolar molecule. Okay, so now it's easy to predict the water solubility of these compounds. We place in the water-soluble category those of these compounds that are polar, which means NH3 and HF. However, carbon tetrachloride and oxygen are both nonpolar and therefore have limited solubility, or they're simply not soluble in water. Some of our ALEX problems have some less traditional solvent-solute interactions we want to consider. So first we want to be able to classify these solvents. First, let's look at some nonpolar solvents. This would be first hydrocarbons. Those things are composed of only carbon and hydrogen. Here's a few examples: benzene, hexane, toluene. You see the only elements present are carbon and hydrogen. These are hydrocarbons, therefore nonpolar solvents. However, if you have some large hydrocarbons that have only one electronegative atom, for example, only one oxygen or nitrogen, even though they are not hydrocarbons, we will consider them nonpolar because the bulk of the molecule exists as nonpolar. To identify polar solvents, we see we're looking for small substituted hydrogens that have only one electronegative atom. Notice in comparison to the nonpolar substituted hydrocarbons, these are smaller, and therefore the impact of these electronegative elements becomes much more significant, and overall we classify them as polar solvents. The final class of solvents are protic solvents. These are polar, but we classify them separately because they have OH, NH, or potentially NH2 groupings. Okay, so water we see has two OH groupings. Here we have an OH group on acetic acid. NH3, ammonia, we recognize has three NH groups. And here we have an OH group on methanol. And these molecules are especially good at dissolving other molecules that have similar OH, NH, or NH2 groupings on them. So let's practice some specifics here. We have sodium chloride, NaCl. This is an ionic compound, and we want to consider the solvents of methanol and propanol. Now we see both of these solvents have an OH group on it. However, propanol has a bigger nonpolar part of it. It's a larger hydrocarbon, and while it may be okay in dissolving sodium chloride, the fact that methanol is smaller in general means that it is going to be the better solvent for NaCl. In the second problem, we're considering the solubility of ethylene glycol, which has two OH groups on it, in hexane versus water. Hexane overall is just a hydrocarbon, so we can classify that as nonpolar overall. Water as a polar protic solvent is going to be much better at dissolving ethylene glycol due to the presence of these OH groups. Okay, let's look at these additional examples. Again, we have ethylene glycol with its two OH groups, and we're going to find it's going to dissolve much better in our ethanol than in this compound here, which is largely nonpolar. It does have one of these electronegative elements, but there's 5 carbons in this, so it tends to be largely nonpolar versus polar. Here we have benzene, a nonpolar hydrocarbon. So we will be looking for a solvent that is also a hydrocarbon to serve as its solvent. Sodium chloride as ionic. We're going to be looking for a polar solvent, which in this case is going to be water. All right, so if we look at this next compound, we have all sorts of OH groups here. A whole bunch of OH groupings or electronegative atoms. So we're going to be looking at something that's primarily polar in nature, and therefore methanol will do much better than this compound that's largely nonpolar. And the last example, we again have OH groupings and a couple of electronegative atoms. So it's going to be much more soluble in a compound such as ethanol that is largely nonpolar and it has that, or largely polar and it has that OH grouping. Our other solvent is a bit polar, and we would imagine this would be dissolved slightly in this slightly polar compound, but that ethanol in general would be better.